we'll head over to our second presentation for today, Beyond Lambda Calculus, Relational Computation by Marcos. And I'm not going to try to pronounce your last name because it's just going to not go right. So I'm sticking with Marcos.
Right.
Welcome
it's
to
Magueta.
Prog Sweden. Yeah.
So, well, it's a pleasure. I'm really glad to be here.
Yeah. You're welcome. Hit it away.
All right. Let me just see if my screen will be there. I think I'm sharing already. All right. So today I have a very bold title. I hope I can present a topic that's very dear to my heart. It's at its core something that introduced me to functional programming back in the day. Funny enough, well, we can talk about that, but yeah. So the topic of the talk is Beyond Lambda Calculus, Relational Computations. So my plan here is to invoke, so to inspire a new generation, if I can be such a dreamer, of new languages that try to aim at the target of relational computations, but using some of the features from functional programming. And I'm going to share a few of them, a few examples, and give more of the path that I had all of this time. So a little bit about me. So this talk, I wish it was about Emacs. I could just talk about Emacs all day. So yeah, I'm an Emacs user, that has to be said. I do functional programming for a living. In fact, I've done it for all my career up until this point. I'm very glad of that. But I'd also like very much relational theory, and that goes hand in hand with database theory. So I've been very eager to research more on the topic because of its foundational history. I do F#, so I do .NET. If I have to, if you point a gun in my head, I can also do C#, but it's not really what I like. I prefer F#. I also like Common Lisp, and I'm not good at it. People say it's the Java of Lisps. I tend to agree, but I think it's fun. I like class segments, where that's something about me, and I'm very interested in semiotics, and I call myself an amateur proto-logician because I'm still studying. But if you want to hit me up, I think the best places to send a message, a direct message, would be LinkedIn. But you can also follow me on GitHub, and there's my email, my contacts all in there. So what are the goals for this talk? I want to present first the problem that I had to confront back in the day when I started researching on the topic. I want to inspire. I want to bring about a new way, a new outlook to our relational world, how we can perceive the world with relations, and how that can help us to make more conforming programs, computer programs, with the things that are present already in reality. And present a what-if scenario. What if we had a computer doing this process for us? All right, so let's start with this quote here, which is, it's basically stating that in a declarative world, you are more concerned with abstract specifications rather than its concrete implementation. So that is analogous to say that when we are looking at, for example, an implementation of a binary tree, or I'll pick SQL, I think it's better. If you are trying to implement a table, like a relation in Postgres, let's say, you are more concerned about how it is normalized, how the table looks, and how it represents structures, instead of being concerned of how it's organized in the disk. If there is something like Zookeeper underneath and distributed, the tables distributed across the disk, that shouldn't matter for the specification of that entity. And then you can stretch that over to programming languages and how they express state, for example. So there's this chart here from the famous book of Peter van Broy, and I think it's a very nice chart because it puts things in a spectrum. You can't really just say that something is declarative or not. So I think it's more of a spectrum that we can observe with the interactions in the state. So in one side we have, for example, less declarative languages and then more declarative languages with its usage. Because no language is just pure that thing, so it makes sense to isolate them by their features. So if you look here, for example, you can do OCaml. Why is it paired with Java? Because you can do stateful functional programming with OCaml at the same time that you can do just functional programming with OCaml, but also imperative programming with OCaml. So it's a language that it's spread over this chart. And then on the other side, you have languages like Prolog and some SQL embeddings that allow you to do relational and logic programming. But you can also do, on the other side, software transactional memory that is very expressive in the state. So this is the importance of the state and how it plays into you, so you can define the program. I think it's a very nice chart. All right, so this is a definition of a program that I have for a project I've been working on. And I was trying to do a relational engine in OCaml. So it's a Perl database that basically I can do relational algebra inside of it and search things in the disk and present them, retrieve data and store data and so on. And then this is basically Nix. So this is my Nix flake. And if you look here, I'm basically defining my package that is built using this function called a Doom, build Doom package, that basically specifies how the program is built using DOM, giving my inputs, environment variables, where the source code is presented, some custom commands. So it's a very nice way to remove the burden of the build system, in this case, to be system agnostic. If any Linux distribution, so long as it has Nix, it can build this OCaml package. If depending on the architecture, I can build different architectures, and that abstracts it all. In this case, I'm even building on macOS. So one example. All right, so some people asked me when I dropped the summary for this presentation about what would be the philosophical listing for me to claim that we are ontologically committed to relations. And these are three of the important people that I think mark a philosophical concept that is very important to me. So classical philosophy, semiotics, and modern logic, more of the analytical tradition. So if you look at Aristotle all the way to Frege, through this is John St. Thomas or John Poinsot, with that started the modern semiotics and later got picked up by Peirce. You can see that the relations are the core presentation of the Aristotle's predication, but it's also the contextual analysis of the sign in semiotics, and they are everything basically in second order logic. So I think this is a very nice picture. I will not get too much into this, but I would appreciate to have a conversation of this if somebody wants to reach out. I think there is much to be said here still. All right, so let's start with some examples, and so we can see how people are using this. So I was researching not long ago about how concurrency diverges from parallelism. It's often not very well explained, and many people have different definitions. And then I came up across this definition from the Sun Microsystems manual back in the 90s, that it basically says that the parallelism is a condition where threads, they're executing simultaneously in time, and concurrency is where they are executing, that is making progress, but the notion of time can be shared. So they are not necessarily executing simultaneously, but time slicing the time for the processor so they can execute. So that would be the representation of concurrency. And now if you think about it, then the only categorical difference that exists between parallelism and concurrency is derived from the interaction of the threads with the state, which is with the time, which is the shared resource in this case. So you could even say that the concurrency in this case is just a relation of is just the representation of the relation in the relationships of the threads with the time. So that's food for the thought. This is an example in OS. I think it's a very cleverly designed language. I think it's a shame that it's not very well known. I used to not know it very well, but I was just checking it and it's amazing. It has so many good features and it's multi-paradigm. So it has many different constructs inside of it to allow multiple paradigms. And it has logic implementations inside of it, but also procedural and functional inside of it. So here we have, for example, just translating this code because the syntax might seem a little arcane. We have a thread that is synchronizing, unifying, that it needs to unify this n variable. And then this n variable is the condition for this or. So this is a disjunction in here. So this is basically the commas in Prolog or Erlang. In Erlang, they have just syntactic meaning, but in here they actually fulfill the goal of branching out the structure of a logic search, right? So what this program will essentially do is simulate give the foundation for a producer and consumer design. So this thread will only start to kick off when you can unify the number n, which is down here, and this thread will only kick off the s, which is needed after this thread is completed. So it's a way to bind things and make things synchronized through relationships of the variables that are shared in this scope. Okay, how are we putting relations to use them nowadays? So this is more of a review of the things that I've seen people doing and how they are doing it. So there's this paper from 2006 that I think it's formidable. It does a very good research on presenting what drives complexity in most of our programs. It's a very famous paper called Out of the Tar Pit. I got cited multiple times already in various conferences. But it presents flavors of complexity. So it presents, for example, this case here, there's more to be said on that, but just for our context, it's suffice to say that it talks about state and control. We are in a functional programming conference. I think most people would realize that, yeah, state is indeed a hassle. We do all of these strategies to hide the mutation of state. Mutation of state makes it very hard to reason about programs, about the logic of things. Control is a little bit weird, though. It's not something that we often think about it because control is more of about the structures that lead that tell the program how to run, right? So how we're supposed to compute something. And then it presents what we want to keep of each paradigm. So it presents logic programming, OO, object-oriented, imperative programming as a flavor of it. And it also presents functional programming as the mainstream alternatives, and then it tries to pick what is meant to be kept of each paradigm. And then it proposes a specialized languages for each scope instead of proposing a general language. So when we are about to start a project, we have a plethora of languages. So we've got here my beloved Emacs Lisp. You've got Java, you've got Microsoft Java, you've got some Erlang, you've got many options to choose, and some of them, they somewhat try to blend the usage of the database, for example, that is supposed to represent this relational outlook to data with the code. So for example, in .NET, you have Entity Framework. But what ends up happening is that Entity Framework, for example, alienates the relational aspect from the main language through ORM, basically. So you're dealing with the internal structures of the language instead of the relational part that is supposed to tame state. So, and it's not the same. It's not the only language that does this. Many others they fall in this category, but some present different outlooks on that. All right, so this is a closure example, and Rich Hickey, on his talk on Datomic, he presents the very idea of bringing the database, trying to not alienate the database and bringing it closer to code, so to the logic of the program. So in Clojure and Lisps in general, there is the concept of homoiconicity. So it's much easier for you to bridge the gaps with some syntax that is commonly shared between both. So in here, some Clojure might look, Lisp in general might look a little weird for most people. So I'll just present more or less what it's being done here. So there's these transactions that we are executing to insert these entities on our database, on Datomic. And then this is a query that we do with relational constructs where we bind the same entity that produces these attributes that we are trying to search. And then it just displays all of them. So it tries to go on the database and unify the tag, the email, and the name that we have inserted. So it should present those in a list. And then here I have a function handler that was basically, there's some other machinery behind of it that is listening to the atomic transactions. And as soon as we insert one of these, it will go through this search the structure and present it on the screen what we have just inserted with the timestamp. So this is basically to show that we can bring the database closer, so the relational parts closer to the code, to the logic of our code base, instead of just having it SQL strings somewhere else. Okay, so there's this other paper that presents something that started to open my mind, which is, it claims that algorithms are basically logic and control. So the logic part would be basically what is to be done, and the control is how it is to be done. So often when we are coding something like a Fibonacci or factorial algorithm, it's very clear that we are trying to bridge the control components is very, it's the core concept of the algorithm. So it's right in the middle, and that's the thing that defines the state management of it. So this separation is attempted, at least to a certain extent, to be done in relational databases like Postgres, SQL Server, Oracle, and so on, but it's not really on programming languages. There is this very thin, we don't try really to diverge the logic from the code, from its control. That's a very weird concept that we haven't explored all that much. Okay, so just to give an example, so this is a exploration that they do in horn clauses for defining relations by recursion. So in this case, we have a contains. So this set is containing here. If it's empty, it's already true. It holds this predicate. This relation holds. If it's not empty, then otherwise you need to split and then apply recursion to construct the subsequent until you get the elements that are contained in it. If all of them hold, then that's true. Okay. But I think Cod knew better. If you look at the papers from E.F. Cod back in the 70s still, he talks about embedding a sublanguage. He was working on a language called Alpha that would be a candidate for embedding into other programming languages that would allow us to do second-order logic, predicate calculus with second-order logic to retrieve data. He later retracted that idea because he saw that it would in the end make data undeterministic. So decisions would be undecidable. You would have relations on top of other relations, and that would make it harder. So we take for granted notions such as, for example, if I say King Canute is one of my ancestors. That sounds easy, like a normal customary assertion, but there's much more to it. You can't express that assertion in first order logic, because you're now quantifying a set of people and trying to define the relation on the set. So you need to find now a set of people that is ordered with ancestry, the relation being ancestry, where you can order you and King Canute in time, and then you can prove that you are indeed, that you can hold the predicate that you are an ancestor of King Canute. In a database, you would encode this with first order logic by doing a closed world assumption, where you basically specify that this is just true. So there is this, and there is this guy. They're both related. They are an ancestor of one another. So it's one way to circumvent this problem. So we can still do it, but it's not nearly as powerful as it would be with second order logic. Okay, so what's the vision then? What if we had a language that could bridge the gaps between the data handling and the logic? So to manipulate the control and the logic, that they are distinct, they are on their own parts, yet they are a cohesive part of a language. So if there's something like that, that's the first question. We would also need a language that is capable of describing relations as part of our business domain, of our business modeling. That would be very helpful. Again, with that idea of alienating the database, we would pull the database to the code. Constraints, we would basically, how we would constrain our data with, be it with equations. There are many strategies, but we do it with types, many other schemas, and so on. So how would we constrain our data? And is there a possibility of abstracting the state? We don't want to deal with the notions of state all the time. That's a no-brainer. And the last is possibly express modularity. So I'm not going to talk about this. I'm going to go on. I'll present this on the demo if we have the time. So let's make a quick review of how current logic programming is. So this is basically an AST. This is a very simple and very minimalistic AST. It's basically using the Bruin indices. I'm not sure if it's Bruin. I'm not sure about the pronunciation. But it's basically using integers to mark the notion of the variable. So we have it defined as a meta variable, so a variable that we can unify and we can find elements. And we have predicates. So predicates, they would be just, they're also another name for them is functors, which are essentially, if they have an arity and they have other terms inside of them to dictate, to say if a value is true or false, if it holds. So a predicate with arity 0 has an empty list, and that's just a fact. So that's an atom, for example, in Erlang and Prolog. If it has 1, then it can have one gap inside of it, and then that's a predicate that depends on that value to be held. If it is, for example, an atom that is inside of it, then it's just a fact. So I could make a quick example here, but I'm just going to keep going and present them in the end. Okay, so unification. So when we're talking about unification, we're talking about syntactic identity. So we're trying to identify how two things are equal by a series of substitutions of infinite procedures that we can reduce the variables to terms. So we can equalize both. So one example of that, and we heard of that on the last talk, was from the Damas-Hindley-Milner type system. It does unification on types. The types are essentially whole, like generic types, let's say. They're essentially holes in the domain that you need to unify to find the possible constraints that you can enforce on that type. So unification is very important for this. So backtracking, it's a very interesting concept that is cooked in some languages like Prolog, that it allows you to explore the difference between the branches in control flow. So if you have like an if, for example, and a variable that's being unified in the if, the variable might hold or not, and then we need to explore the possibilities of the branch going on the then clause and on the else clause. So you will have to test the cases and go back on this bifurcation. So you are here, and then you go here, and then you explore, and then you discover that you fail, so you backtrack, try the alternative, and go on. Another one is determinism. So we introduced non-determinism by basically exploring those choices, right? So when we are looking at a branch and we look at let me go back here. When we're looking at a branch, we might go back and then we have to undo side effects that we might have caused on this. So we would have to go back and then we explore another alternative. The operator here we are talking about is choice. Choice is the definition of a non-deterministic algorithm. So we're exploring a list of values that are possible solutions for this concept. So if there's only one, then it is deterministic. If there's multiple choices, there's multiple outputs for it, then it is non-deterministic. Okay, manipulating lists often it results into non-determinism with constructs. If anybody is interested in implementing something that is just logic programming, there's this paper. It's actually a book, more or less, that just gives you an instruction set, and it explains very nicely what we can do about it. In fact, we're doing that now. Me and a group of friends, we're implementing a language called Karuta that tries to implement this with bindings for manipulating data and first-order logic as well. Okay, so now what if we change the approach? What if we mix both? So what if we pick the good things of functional programming and the good things of logic programming, and we merge both? So that's a question that's been on the debate for quite a long time already, but just now it has started to pick up momentum. So one of the core things that we would have is higher order pattern unification. So I did some sort of this AST here. So you can see that it grew substantially with the Lambda calculus constructs. So we will have now a free variable, a meta variable that we already had, a local variable, and they're all with integers. So we don't need to have the parameter here in the argument for a Lambda. And we have essentially a term for the Lambda, applications of things that we can reduce to lambdas, and terms that we can apply to those lambdas, and in the end, the predicates just like we had before. Now, if we are to unify this, it's easy to see that we now have lambdas. How do you equalize two functions? How do you unify and make the two functions equivalent? Well, you need to do beta reduction. So now it's another problem because you now are trying to better reduce functions before you start unifying. That we have algorithms to do something of the kind. We have this Gerard-Way algorithm, and it's semi-deterministic. So it's good. It's very efficient, and it's very simple at its core. It just produces more branches and more data so it can test. So in the end, it can just prune the data it doesn't use, but it's still semi-deterministic. We do, however, have decidable parts inside of our program that we can unify. So for example, variables with integers, we can unify them to the integer that we want. So we can unify those first. And in fact, that's what the linear algorithm that I forgot the name now, but there's a linear algorithm that does that, and it's used inside of Isabelle and Lambda Prolog to do it. Okay, so what's the gain of this? What do we gain by doing all of this? It seems a lot of trouble. There's this nice property with functions, which is we can analyze their injection. So if we have one set and we have another set, and each value of one set maps to the codomain, maps to at least one element of the codomain, to different values, then it is we call it a one-to-one function. It's an injection. If it's a surjection, means that there's some values on here that map to the same value. So one function that we could say, for example, that is like x squared. You give -2 and 2, and it produces the same value. A bijection would be that they map exactly to 1 because they are 1-to-1 and on 2. So each element of this domain is mapped to this. So in theory, this is the necessary component so you can invert a function. If you can invert a function, think of the possibilities that you can do with it. Look at this example here. We have a pretty print function that can receive an AST. How is it implemented? It's unified with a source that we don't know. We want to discover the source code that produced that AST. So we unify the parse function that we already have implemented with the meta variable source with the AST. It produces us a unification of it, and then we can now print the source because we know a way to print strings. So this is a very nice use case and to showcase how powerful the idea of manipulating this the relationships between the functions as relations yield us. So there's this paper that I read, and it's absolutely beautiful, that they describe a way to implement a language that is a relational calculus. So they themselves implemented their own. So they go deeply into proofs, and they make usage of it's the best usage I've seen of Church-Wasser for trying to identify equations that, for example, produce the same values. They discuss their technical challenges, and they present an organized introduction that is very easy to grasp if you don't know really much of the theory yet. Okay, so now let's try to take a look into some examples. So I've got some here, and of course, an inside of Emacs. So let me do that. So first of all, we have this web scraping example in Prolog. Let me just increase it a little bit. There we go. So this is from a blog of a guy that I really admire. His name is Benjamin Johnston, and he wanted to prove the power of Prolog. And he basically did an example where you had an HTML page, and you had a table in it showing the cities and their temperature in a weather forecast scenario. And then he defined this relation where you basically pick, I think it is easier. So this element is because of a library we're going to use. So it will break down the HTML elements and then try to observe in the children and look at the relations between the city and the weather and the temperature. In the end, we just grab the page, which is here. We grab it in a data string. We feed it to this load structure function from that library that basically loads HTML, and then we just feed the page structure to trying to find the city forecast. Results, these are all we find. So it's a very elegant way to do web scraping that is treating the web page, the HTML structure, as a database that we can query data from there, looking at the relationships in the case of positioning of the things in the HTML structure. All right, so another one. This is in Mercury. This is the common implementation of the dining philosophers using one semaphore. So I'll show more of Mercury, but this is just to warm up. So we define a predicate where we receive a I/O. So Mercury is a typed language, and it tries to do it tries to have some purity discipline. So in Haskell, you would have something like a monad I/O, where you would handle the entire context with I/O whenever you have I/O in your code. And then you would have to propagate the I/O usage to the other functions that are on the other side. This symbol here, like exclamation I/O, it's basically a sugar syntax for these two. So it's basically destructive input and unique output. So we're basically defining these two in a single variable. I think it's easier to grasp. And then we define a semaphore, we lock, then we emit a signal. We define the philosophers, so Plato, Aristotle, Descartes, and Russell and Sartre, and they're all sharing the lock, and they're all sharing the I/O, but this I/O goes changing its structure. So for example, this function mutates I/O, let's say. So it will produce an I/O instead of I/O0 that would come from this, it would be I/O1. And then I/O2, I/O3, I/O4, because there are different productions of I/O from the input and output. So you would always have this interleaving of the I/O following up. So this is our entire program. It's very easy to read and very nice to reason about it. You can basically see that they're all sharing the lock and they're all spawning philosophers. Now, if you look here, the other predicates that we have here, the philosopher, is basically being used here with as inputs. So we're giving inputs of the semaphore, the philosopher, and I/O. And we are, you can ignore this. This is the Mercury. You have to type the determinism that is expected out of the predicate. I can get more into that in the other example. So we're passing down the who is the philosopher, the lock, and the I/O, and then we get the name of the philosopher. We present it to the screen, so we cause the side effect on the I/O, an effect on the I/O, and then we wait on the lock, get the fork, and then we see if we have acquired the other fork. If so, we proceed into this branch where we set the global fork. So this is another relation that we have, another predicate that we have down there. We emit the signal, blah, blah, blah. I'll not get too much into this, but the point is, it's very easy to look and read the code that otherwise would be somewhat complicated to reason about the state change in a very simple, readable way. So you're clearly seeing what's going on here by just taking a look at the shared components that are being used. So in the end, we just do our configuration. We express the modes that we take care of. And then we just have the names. That's very simple. So this was just an introduction to Mercury. Now, let me show something that is perhaps more interesting. So I have on here a couple of examples. So there's this example that Wilbur likes to use with quines. So this is for mini Qumran. So Wilbur has many, many nice talks, and he's a very clever guy and very nice to see. So I'm going to use chess scheme to produce a program that can produce other programs for me. And I think this is the demo, not helping. Let me try again. Geyser scheme, well, chess. I am on the same folder. I think the path is not right because schemes imports, they are basically relying on the local path where I spawned the repo, and since I started Emacs in the upper directory, I will not be able to import it here. So I'll just explain what it does. You can check the 99 ways to say I love you. It's a program that it's more or less like this. You would put 99 here, and then this will try to unify the variable q with some interpreter, and this is something that you have to do on your end. So eval expression with this o, so eval expo, and then you have the q variable that you want to unify, so that would represent one of the variables that you are searching with a random context that's empty in this case, with this result. So if the program evaluates its logically equivalent to this, which is a list with hello, Func, Prog, Sweden, then it would produce programs, in fact, 99 programs that can evaluate to this. It's a shame I can show this because it's a very nice use case of it, but let's move on. So let's get into I was talking about Prolog, so I have that backtracking. So this is Prolog. Just activate. So this is Prolog. Prolog is very interesting because we're defining these edges, and they're just simply facts. This is what I said about A having 0 arity, the same way the B, C, and the rest do. An edge has 2 of arity. So I could make a search, let's say, edge with A to B, and then I would basically be asking, hey Prolog, give me the nodes that have an edge to B. So it would be A, it would be just A in this case. If it was C, then it would have B, and then again just B. If you had E, it would have D, and so on. So you would have the alternatives in that. And then you can make a predicate that you can evaluate the path. So you could say, this holds if you have an X and Y where you want to get a list where the head of the list is unified with the first element of the edge with an intermediary element Z, and then this intermediate element you can recur using recursion with the Y that we want to search. So we are targeting Y, constructing the path along the way with this intermediary value. Okay, now let's just do some Mercury, and I hope I'm not running out of time. All right, so I have this code here, so let me just activate Mercury mode. So Mercury is a very nice language. So we can do, we can declare our module, then we implement. Unfortunately, the module needs to be the same name of the file. And then you would have the modules that we want to import. In this case, I'm just importing IO, int, list, and strings. And I'm getting defining my predicate, that is the entry point, which is the main, that is deterministic. And then the implementation is essentially just print hello from Prog Sweden with a new line. So let's try to run that. sh. Okay, so I should have Mercury. This is the compiler. So we can compile Mercury to C#, Java, the Bean, Erlang. I'm not sure if it compiles to the Bean bytecode or Erlang. We can compile to C#, C as well, and assembly. So it's a very versatile language to interrupt. It's very powerful. So let's use high order M. Compiled. There we go. Got some warnings because I'm not using the imports, but that's fine. So higher order. There we go. Hello from Prog Sweden. Easy peasy. Now, let's define a predicate that does something more with it. So I already said about the functions that being invertible, right? So we can be able to find stuff. So let's define a predicate, pred, where we're going to have an addition. So we're going to add things. It's going to be deterministic. So we always have an output that is single. That's actually a lie because you could do something but let's focus on that to make it easier. So we're going to receive an integer where we're going to get the first integer as an input. We're going to get the second integer as input as well. And the third integer will be our output. So there's no distinction in a predicate of the things that you give. There is a distinction on the things that you give as input and output, but you don't get a return out of this. You're not like a function call. Although Mercury also has functions. I'll show them in a bit. So I'll remove this. And now here we're going to do define the predicate here, which I forgot. So we're going to add. We're going to get A, B, and C. And the definition, the implementation of this is essentially that C is equals to A minus B. That's it. So that's our predicate. It's defining a relationship between the C and the A and B with add. So, all right. So how do we call that? We can do add with A, with 5, and then put an X, which is our result. We're going to put a comma. So it's do this and this. And then instead of doing this, we're going to write an int. So to write an int, it's very simple. It's just going to do this. And in the end, we can also do io.newLine, where we pass the io. So this should do, this should find the value here, which is 10. So let's just run it. There we go, 10. Now, what if we change our predicate and we put out here, and then we put in here? So we're just changing the positions we're looking for in this definition here. So now, if we put 5 and put x here, what other number added up with 5 gives you 5? Well, 0. So let's see. There we go, found 0. What if I change to, let's say, 10? 5. So you can play around with this. You can define many different approaches. But this is just to show that you can manipulate whatever you want in here if you have different modes prescribing the input and output in Mercury. So you could do that. Okay. Now, just to end with this, I think this is the part that most people wanted to see, which is how to do high order functions inside of a language like Mercury. You have support of that. So let's remove this here. Let's remove that. So let's define a way that we can iterate over a list. And then I have this code here. So I'm going to just copy it because it's too much so I can type. There we go. There we go. All right. So this is a code I did off camera with where we're trying to find matching functions. It's silly. It's just a demonstration. So we have candidate functions where they do different calculations. So one adds the y with 1, blah, blah, blah. This is a type of a function, by the way, but this is also a value. So if you look here, we can define function types like this. So this is a function type. It's a function that takes an integer. Notice the lack of mode here because it's just a function. It's not a predicate that outputs an integer, and you have an input. This is an in this list because that's part of this predicate. So you're taking lists of functions that go from int to int. It's deterministic. So this find matching functions will essentially run a list filter that is semi-deterministic with predicates that are semi-deterministic. And it will try to evaluate this equation that yields 10. So if the equation yields 10 with the inputs that it can unify, then it will yield that as a valid function on this candidate functions. These are candidates, and this is the equation that we're searching for. So we're searching for this higher order equation. We put 5 because that's the value we want the functions to be solved for. And then we call that to call the functions. And then we say, this is our matching functions we're getting as an output. We do an if. If it's empty, we just print there are none. Otherwise, we fold and show which one of them that indeed they match with this. In Mercury, this is a way to format structures so you can show. So let's just run that, and let me bring that again. So I'll just compile. Nothing exploded. There we go. So it found 1, and indeed, there's just 1. There's just 1 here. So it's this 10 minus 5 yields 5. So if we put 5 here, another function, so it found 2 now. So the fact is you have now a list of them that you composed, and now you have access to the function that you refined through some process like that. If I wanted, I could remove this, for example, and try to unify for values in a constraint. So that's something that some languages do, which is narrowing. I think Curry, which is another functional logic language, does. You can narrow by equations and constraints to reach a state that you want to deal with. Okay, so that's it. I think I went through a lot already. So we can end here, I think. So questions.
Thank you very much, Marcos. Thank you very much. So far, no questions in the chat. I'll shoot one immediately. Mercury, do you know if it's used in any production environment or any like, is anyone using it for real, or is it just used in university for research?
There is, in fact. There is a I don't know if they still use it, but I know that Prince, the PDF formatting tool, it uses Mercury to basically do the relationships of the layouts. Because when you have a web page with HTML and CSS, it's not very easy for you to do page break, right? So they use Mercury to define that kind of stuff. And it works very well. I heard things about the government of Hungary using that as well, but that seems to be a use case of some department of the government doing research with medicine, basically. So it's Department of Health, something like that.
Yeah. One more question: is Mercury the one, or is like? I'll rephrase the question. Which language you feel is closer to the dream in your experience? Is Mercury the one, or is there anyone closer?
Sorry, can you repeat which language?
Which language you feel is closer to the dream in your experience?
Right. I think in my dream, Mercury is very close to that. But I don't think it expresses some of the things that I like. I come from SML, F#, OCaml. So modularity there is king. I mean, maybe not in F#, but certainly it is in OCaml and SML. And Mercury doesn't implement that all that well, I think. I might be misjudging the language, but that's my perception of it. So I think OS is somewhat more interesting at that. But yeah, I think these languages tend to be more on that side of the modularity, right? But I think they're good. I would totally use Mercury to do my personal stuff. And as I said, it compiles to other languages, right? So it's a very nice approach.
It is. I never heard of it before. I quickly Googled while you talked about it and found the wiki page and just scrolled through it quickly. Yeah. Thank you for sharing Mercury and also OS. I mean, we haven't had that on here, so thank you very much, Marcus. Let me see. I don't have any more questions in the chat. So again, thank you very much, Marcus, and thanks for participating and sharing in Func Prog Sweden. Thank you very much.
Okay, I appreciate. Thank you very much.
You're welcome. And now we're like on the final note for this year. We'll be back next year with more Func Prog Sweden and more sharing and more good presentations and more fun stuff. And until, have a nice Christmas and a happy New Year, and then we'll see you next year. Bye for now.